Okay, everybody, thanks for showing up to our reading group. Today we have Reese Kneeland presenting his new preprint with us. Reese is a PhD student at University of Minnesota in the Nasolaris lab. And just a quick comment that we encourage open discussion. So Reese, if you're okay with it, if everybody is encouraged to interrupt, ask questions, you can use the chat, or you can interrupt audio-wise to ask for clarifications or just open questions. And of course, we'll discuss at the end as well, but I encourage active interruptions. Those are fine as well. And Reese, you can go ahead.
Yeah, I'll build on that just by saying feel free to interrupt me at any time. I'm gonna try to tell a story here, but it's gonna need to have people understand every sequential part. So if you don't understand something, interject and we can talk about it. And I can jump back and forth between my presentation here and the actual preprint. So we can sort of have a little bit of a looser presentation style. But my paper today is titled Brain Optimized Inference Improves Reconstructions of fMRI Brain Activity. And the central thesis is we have all of these great decoding papers that have been set off by the release of NSD. And so while this is another decoding paper, the goal here is to do something that pushes the decoding space in a little bit of a new direction. And so it's not just another paper that does sort of the apply machine learning to brain data and spit an image out approach that the majority of papers in this space have been tackling since the release of NSD, which I'm sure is widely known within this community, is a big neuroimaging data set of fMRI image pairs. So I won't spend too long explaining this. I think people in this club are generally familiar with what NSD is, but it's a large data set out of our lab, me and Thomas's lab, where we have tens of thousands of scans of fMRI brain activity matched with images, which has allowed us to do machine learning and do some decoding approaches, which, like the MindEye work that has come out of the MedArc lab, we've seen lots of success in this field, and we generally get a lot of successful decoding results by applying machine learning techniques to this data. But all of these decoding approaches, they have some problems still. And just to list a number of them, we are currently not enforcing a reversibility constraint. So the premise of this is that if a reconstruction is good and is faithful to the image that has been encoded in the subject's brain activity, then we should be able to accurately predict that brain activity by running our reconstructed image back through a brain encoding model. And this is a constraint and an idea that no one has really looked at in the decoding space yet. And that's part of the main idea of what this paper is going to tackle. So the other idea that's motivating this is that the image feature metrics, such as CLIP, pixel correlation, structural metrics, all of these things, AlexNet, these image feature metrics that are used to both optimize and evaluate these decoding methods are usually a poor proxy for the human visual system and by people's perceptual similarity measures. So we're going to try and explore our brain optimized metrics to try and put forward an alternative to these in a new way of optimizing for something that is closer to perceptual similarity. The other thing that we're going to try and do is capture a distribution with a measure of uncertainty in our decoded distribution. All of the current decoding methods have no way to capture or represent the neural uncertainty that is typically associated with brain data, as well as just the perceptual state of the observer. So we're going to try and implement a way to at least represent that uncertainty and lay some groundwork for future work that can more accurately calculate that uncertainty. So we also want to just lay the framework for extending these models. I think it's pretty interesting to be able to get images out of brain activity, but if we look at sort of where this research will eventually lead, what sort of technologies can this research develop, all of the current decoding research is based on vision decoding, which, if it worked perfectly, the best thing that you would end up with is you would have essentially a brain camera, right? I would have your brain, and through the decoding of your brain signals, I would be able to look through your eyes. But that's not as useful of an objective as some of the other decoding approaches, because I already knew what you were looking at in the scanner, right? I showed you the image. And so more interesting decoding approaches could be applied to mental imagery or dreaming or situations where we don't know what the ground truth stimulus is. But these also have limitations, such as the higher uncertainty, the need for a way to capture that, and also the difficulty of optimizing without a ground truth image. So a lot of the motivation of this work is laying the groundwork to extend decoding methods to these more interesting domains. So What we're going to show today is a new brain correlation metric. Well, it's not really new, but we're the first to use it in a decoding approach like this. So we're going to use it to measure the alignment of an image to brain activity, allowing us to essentially score an image with respect to the brain activity target instead of the ground truth image that was shown as a stimulus. We're also going to introduce a new algorithm that optimizes the inference process directly against this new objective to improve our results. And then we're going to output a distribution of images that is described by the diffusion model parameters, with the width of that distribution representing a meaningful measure of decoded uncertainty. We're also going to test out a preliminary stopping criterion for estimating that uncertainty for the distribution width. So to talk through these problems a little bit more and lay some more groundwork, the measuring image similarity has been a long problem in computer vision, right? We have two images that a human can look at them and say, wow, those two images are really similar. But to get a computer to come up with a similar result that aligns well with human perception is incredibly difficult. Taking correlations in pixel space are extremely sensitive to aberrations. Lots of the neural network models, even the more recent ones like CLIP, are very sensitive to adversarial examples where we can manipulate image pixels to screw up classification tasks, or just the different manifold spaces that these models land in is generally not very well aligned with human perception of looking at an image. So what we're going to try and do is introduce a new metric as an alternative to this. We're going to call this metric brain correlation. And essentially the way it works is we have the original brain activity of the subject who is looking at these images in the fMRI scanner. We're going to use that as our target. To be specific, we're going to use the average of the 3 trial repetitions in NSD as the target, just because that is the most faithful and refined noise-free, well, not free, but it has a reduced noise just from the averaging procedure. So it's the most faithful target to the brain encoded representation of these images. And to score against that, we're going to pass our images through an encoding model that has been trained on the NSD dataset with these brain optimized features. So the idea is that by passing it through a brain encoding model, the machine learning encoding model is going to extract the features not that have been trained on an image dataset, but that have been trained to be sensitive to the brain activity patterns themselves. In other words, if the brain activity signal is changing with respect to certain image features, the model will learn those better. This should hopefully give us a metric that is more faithful to brain significant, or by extension, perceptually significant features. To do this, we're going to use a model that came out of my lab. Model's called GNet. It's a convolutional neural network, but it is trained from the ground up on NSD, so it has no pre-training on anything like ImageNet or other image data sets that might bias its feature extraction. So it's also sensitive to the receptive fields of voxels, so it's relatively good at predicting voxels in both early visual cortex as well as higher visual. And because it has the sensitivity to both the structural and semantic elements, it's a good holistic model to perform our evaluations on. This is a hefty slide, so bear with me. It's a little complicated and you don't need to understand all of it, but the idea is essentially starting from the left. We're going to use a base decoder, and for all the results in this paper, we're going to use MindEye as the base decoder. We're going to use that to decode a clip vector and a structural base image, which is going to be converted to a Z vector using just the stable diffusion autoencoder. So that right there encompasses most decoding papers. You could feasibly slot any base decoder that can spit out a clip vector into that approach, and this algorithm would still work. So once we have a clip vector and a structural vector that essentially describe a distribution of images when passed through a diffusion model, we're going to sample a bunch of images from that diffusion model, run them through our encoding model to create predicted patterns of brain activity, and then going around the loop, we're going to then score those patterns of brain activity with our brain correlation metric against the original pattern of brain activity. And we're also going to run this check, which I'll talk about a little bit more later, which is a stopping criterion defined by an autoencoder. So once we have met the stopping criterion that I'll talk about later, we will output our image distribution that we currently have. So whatever diffusion parameters we've specified, the clip vector, the structural vector, and then the strength parameter, which defines the width of the distribution, we're going to call that our output. That's our output distribution. But if we haven't met the stopping criterion yet, what we're going to do is we're going to take the images that we sampled from the diffusion model that scored the best in respect to brain correlation, and we're going to use those as our structural input for the next batch. So in essence, we're going to refine the outputs of our distribution by taking the best images from every batch and using it to alter the next batch. And every time this loop repeats, we're going to drop that strength parameter so the distribution width is narrowing. I'll also outline this a little bit more in a future slide, but the goal here is to essentially refine the moving target of our brain correlation metric, and we're optimizing for that, while also reducing distribution width until we hit a threshold. So we're accomplishing two things for this. We are optimizing the reconstructions with respect to brain correlation, which will hopefully improve them. And we are also optimizing the distribution decoded width. So we are outputting a distribution that is meaningful not only in its content, but also in its width, that will hopefully represent a measure of neural uncertainty. So to talk a little bit more about distribution control, this is really what that looks like. So I have some examples here. There's no brain data in this, just using the image in the bottom left as a seed to show you sort of what the strength parameter does. So if we use a high strength parameter, we're encompassing only the semantic clip-based information from that image and sampling from a diffusion model with that information. So there's no structural guidance on this left column. And what we see there is that we get pretty consistent semantics, but very wide variable structural content. This produces a very wide output distribution of images. We can have images that look very different from each other. As we drop the strength parameter, we're encompassing more and more of that structural information. And what that does is make the images more like the structural seed that you give the diffusion model. And this, in essence, is reducing our distribution width because the images are becoming more and more like each other. So this is the mechanism by which we are controlling distribution width in our output. And narrower distributions will look more like the right column than like the left column. So
Can
to
we,
show
can we go back
yeah,
one more slide? I just want to make sure I'm understanding this
this is a
schematic.
hefty slide. Yeah, please ask questions.
Yeah. So basically you start with I guess the average across image repeats voxels, and you feed
Correct.
it into the base decoder, which is MindEye.
Yes,
And then you get C, which is that the last hidden layer of the clip
correct.
model, right? And then
Yes.
Z is what?
Z is the low level blurry image that MindEye spits out. And we use that as the structural input to a diffusion model in the same way MindEye does.
Okay, so the image to image kind
Yes,
of
this is the image to
approach.
image versatile diffusion pipeline is the way this is implemented in the code. Yes.
Cool, cool. And then you get a lot of different batches of images, and
Mhm.
then you feed this to an encoding model, which is GNet. And
Correct.
this is pre-trained and frozen, or are you training them both at the same time?
It is pre-trained and frozen.
Okay. And then you get the estimated the estimated voxels. And then can you tell me, can you go through what happens after you get these estimated voxels?
Yes. So the top little box there with all of the different eyes is sorted brain correlation scores for all of the images. So that we're calculating all the brain correlation scores, and we're taking the images with the best scores and passing them in through the stable diffusion like AutoKL encoder that just makes them into a Z vector. And then they're going to serve as the structural input to versatile diffusion for the next batch instead of the one output by MindEye. So the MindEye outputs only count for the first iteration for the Z vector, those like blurry low level images. And then for all future iterations, we're going to use the best images from the previous batch for the structural guidance. And the
These
reason
are the
there's
images that
four,
are output from like in the top right, using both the C and the Z.
yes, the clip vector is fixed constant that MindEye decoded, and the structural guidance is changed every iteration to update with the new images that have the highest brain correlation scores.
Mm-hmm.
And the reason there's 4 batches in the top right and 4 little lines coming out of that brain correlation score box is because we're using essentially 4 parallel searches to try and avoid getting stuck in a local minimum. Because the problem here is that if you use only one, then you might end up with an image that is essentially a local maximum on the manifold of possible image scoring. And so if you keep using that one to refine your structure, you will get images that look only like that one. Whereas in reality, we want generally well-performing images that might lie across a variety of manifolds. So just having a couple of batches helps us avoid getting stuck in that local minimum. I suppose this is as good a time as any to talk about the stopping criterion as well. So this is the bottom box below the brain correlation scoring metrics. What we're going to do is the problem that's motivating the stopping criterion is that when you pass images through a brain encoding model, it produces a set of predicted voxels that contain no brain noise, right? Because if the encoding model was trained to only associate the voxels that were meaningful in terms of image features, then it's not going to spit out any random brain noise that we see normally in fMRI data. And so if you take like the variance of voxel-wise data across real brain data, it's going to be much, much higher than the voxel-wise variance of encoded brain data. And this is a problem when we're trying to compute a stopping criterion, because really what I want to know is when does the variance of our predicted brain activities match the variance of our actual brain activities? And so what we're going to do to remedy this issue is we're going to pass the original brain data through a denoising autoencoder that the way this was trained is just to map regular brain data to the space of the encoded brain data. And we do this by using the beta primes, the encoded patterns of brain activity as an optimization target when training the denoising autoencoder. So in essence, what it's doing is removing the brain noise and keeping the signal. And then we're computing the variance of the original NSD trial repetitions that have been denoised against the variance of the encoded patterns of brain activity. And when those match, that's our stopping criteria. This has some problems, which we'll discuss later. Most notably, that brain noise is probably very important for estimating neural uncertainty, and this method destroys it. But this is what we're using as a preliminary method for this work here of trying to estimate a stopping criterion. We can talk more about that later. Do we have any more questions on this slide while I'm here? Looks like we have some in the chat.
Yeah, so I'll basically rephrase Syed's question here of, so it's a repetitive process for the same input brain activity. So the voxels are always the same. The mind eye is always the same. Even the encoding model is always the same. What changes is specifically the image to image input into the diffusion model,
Correct.
the versatile diffusion model.
Yes, this is an iterative inference process that for the same pattern of brain activity, we're trying to reconstruct the same outputs. We're going to do it iteratively until we meet our stopping criterion. At every iteration, we get new structural guidance that is hopefully more brain aligned, and we use that to inform the next iteration.
This V, it starts out being like the blurry input, but that's only for I equals 0. After that, it's always actually a somewhat semantically rich image because it's gone through the diffusion model, but you're always using it as the image to image input.
Correct.
So why don't you also modify C? Why is it that you're modifying C and Z?
So in a previous version of this work that I wrote a paper under the name of Second Sights, that was happening. We were iterating the C vector, and we used some like sliding window, like rolling momentum parameter to adjust it. And what we found is that kind of works, but it's also pretty unstable. And the whole idea of this pipeline is that for the clip vector can only store so much, right? It's a pretty wide description of a family of images that a clip vector represents. And the base decoders like MindEye are already doing a pretty darn good job of estimating that clip vector. And so the actual work of optimizing this reconstruction, there isn't much left to be done for the clip vector, is what we've found. And we can try and optimize it a little bit, but it adds a lot of complexity when you're trying to augment the clip vector, when in reality, a single clip vector is wide enough to describe all of the images that we might want in our decoded distribution. And just by sort of pointing the diffusion model in the right direction using the structural guidance is enough to refine the reconstructions as to the degree that we're hoping for.
Yeah, it's just, I guess I'm wondering, like, the versatile diffusion model is going to be pushing this semantic content from the clip vector into the image reconstruction. And then you're putting that as the new input for the image to image. But how the image to image works is that you're noisifying it so that it can be one of the first like time steps. And so like the versatile diffusion model is interpreting the Z as basically a blurry image, even though it has gone through previously with the clip vector to get more rich. So
Correct.
essentially, you're optimizing to find the best blurry input, even though the blurry inputs have been like enriched by the clip vector through every loop.
Yes, and the other detail that's important to note here is that as the search continues, the strength parameter drops and less noise is added to that image over time, which means that the images get less blurryified every iteration. So as you converge further, those semantic details that are being injected into that image are being preserved more and more, and your output image distributions will be more and more like that structural guidance. So in this way, it is kind of refining the semantics of your image as well as the structure, but it is doing it only incidentally and not methodologically.
Uh,
Looks like okay. Do you have any more before I can ask a few more questions from the chat?
um, yeah, let's go to the chat. So how large is the model? And Connor asks, would it be possible to directly optimize image generation to minimize encoding error?
So I'll start with how large is the model. The beauty of this pipeline is that there there is no new model being trained here. This whole process happens in inference, and every model is pre-trained. So the MindEye based decoder is pre-trained, the GNet model is pre-trained, the autoencoder is pre-trained. So all of this happens during inference, this search process. But in terms of the models we use, the MindEye decoder is its own thing, which maybe Paul is more qualified to talk about how big that is. The diffusion model is versatile diffusion, which is a relatively large diffusion model. It's pretty standard for diffusion models. The GNet encoding model is, I'm trying to think of the actual parameter number. I don't have it off of the top of my head, but it's relatively similar to a model like AlexNet in terms of its like parameter space. It's just that it has been not trained on large image data sets like AlexNet. And the denoising autoencoder is relatively small. That one's a multi-layer perceptron that is just going from brain data to brain data. So it only has some layers of like 1,000 nodes or whatever. For the next question, would it be possible to directly optimize the image generation somehow to minimize brain encoding error? I have thought about this, and the main thing that has stopped me from pursuing it is just that I don't have the resources to train a diffusion model really, or to significantly fine tune it to have a brain conditioned generation. Because right now the diffusion models are clip conditioned, and I assume this is what you mean, is that you want the diffusion model to be conditioned on brain activity directly. And I would love to do that, but there are a couple of problems, notably that clip is a very nice hyperspheric manifold space to where you can interpret very easily between points in it. And that allows you to have a very rich descriptions of image content that the diffusion model can easily pull from. Brain activity is not nearly as nice of a manifold. There are manifolds, but it's not trained to be uniform in the same way that clip is. And so it would be difficult to condition on that, I suspect. But it is a cool idea that I would potentially like to explore in future work.
I think
Thomas also
another,
says in past work, we've conditioned a GAN model directly on brain activity vectors. That was some work that Thomas and Ghislaine, one of the other co-authors of this paper, have worked on. So it is possible to do it with that, but diffusion models are trickier.
yeah, another thing is that like when you're training these, specifically these diffusion models that can accept clip inputs instead of like the text prompt, right? Like you generally would be fine tuning with many samples. And I'm not sure how well it would work with the limited number of NSD samples. It might be
Mhm.
enough, but it could also be that like you need a, a wider like distribution of images to fine tune the model well.
Yeah, I would also second that. It's typical for diffusion models to be trained on hundreds of millions or billions of images, and we have tens of thousands of fMRI image pairs. So you would definitely be limited to fine tuning an existing diffusion model, but fine tuning becomes much more difficult when you are completely changing the conditioning space. And so I think that would be tricky. Yeah, Thomas says you have to use proxy data from the encoding model to train a brain condition diffusion model, which is right. But the when you use proxy data, you significantly limit the complexity of your image space. And so I think your diffusion model would still have somewhat mediocre training results if you did that. But he's right that that's the only way that you could get the scale right. Can you share on how the similarity score is which converted to Z? So I believe you're referring to the brain correlation scores, Syed. So the brain correlation scores are defined on this earlier slide. So what we're doing is we're just taking a Pearson correlation between the voxel values of the brain data. And this is done voxel wise, but then average. So we're just taking the average Pearson correlation between two voxels within the predicted pattern of brain activity and the averaged trial repetitions of actual brain activity. And that gives us our score. So we're just measuring how similar is our predicted brain activity to the actual brain activity. All right. Any more questions on the slide?
One more question for you.
This
So
is the beefiest slide. So if you have questions now, would be the time.
yeah. So can you clarify a bit more? So this green denoising autoencoder, right? So
Mhm.
you're comparing like why do you need that and how are you like can you repeat how you're using that exactly?
Yes. So the core problem that this is aiming to address is that we want to estimate when to stop this refinement process. If we continue this iterative process forever or until we drop the strength parameter to zero, there are a couple of concerns. One is we would overfit to our encoding model through this optimization process. Two is that we would overshoot the amount of decoded certainty we really have. Like brain data is very noisy and because of the limited resolution of fMRI, as well as just the process of abstraction that your brain is doing when it interprets an image into a perceptual state represented in brain activity, all of that carries some uncertainty. And so we don't want to output a single image. All of the existing decoding models focus on outputting like a point estimate of just a single image that says, here is our decoded image. But I don't want that. I want a output distribution that has a meaningful distribution width, because I know really that the pattern of brain activity is not specific enough to warrant generating a single image. And so when we want the distribution width, the goal is when do we stop? And so the idea is let's compare our encoded patterns of brain activity to the actual patterns of brain activity, because these have variances. There are variances between the multiple trials of a person saw the same image 3 times, and we have 3 patterns of brain activity. So the variance between those 3 patterns gives us some measure of how certain the neural data is, right? If the brain data varies X amount from repetition 1 to 2 to 3, then we have some measure of uncertainty to capture there. But the problem is that when we pass images through an encoding model to predict patterns of brain activity, there is no brain noise. And so the problem is, how do you compare something that has a variance of 0.0001 with something that has a variance of 0.02, right? These are off by 2 orders of magnitude. And so trying to compare variances between those becomes impossible and not useful as a stopping criterion. So what the autoencoder is doing is it's removing the brain noise that the images are not associated with. It is training it is a model that maps original noisy fMRI brain data to noise-free brain data that looks a lot more like the beta primes that we're making with our encoding model. And the idea is that now we can actually compare them. I can say, is the variance of my batch of predicted patterns of brain activity, right? If I generate 16 images, I can take the variance of those 16 predicted patterns of brain activity and compare it to the variance of my 3 trial repetitions. And when those are the same, that's when I want to stop.
I would just say that the autoencoder does it. It's not noise free. It's just sort of less noisy than the original beta.
Yeah, it's trained to map to the same noise properties as the predicted beta primes, which is in practice much, much less noisy than the actual brain.
There's basically a scaling issue. You get a certain amount of variance in the outputs of the encoding model for a certain value of the strength parameter. And what we're trying to work on now is for what value of the strength, it's kind of, if the strength parameter is lambda and brain noise is sigma, there's some transformation between sigma and lambda, and we're trying to figure out how to get the scales right. This autoencoder was like a first attempt at
Yes.
balancing those scales, but it's imperfect for lots of reasons.
Yeah, and I'll talk more about those reasons in the future, but it is very preliminary, the stopping criterion. It is the least fleshed out part of this whole pipeline. All right, any further questions on this slide?
There's a new question from Connor in the chat.
The points about conditioning on brain data make sense. I guess I was thinking more about adding a brain encoding error as an additional loss for fine-tuning the diffusion model. I get that fine-tuning a diffusion model may not be feasible though. That is probably more practical than abandoning the clip space entirely. It's certainly worth looking into. It's not something I've explored, but I have had ideas bouncing around in my head about how to compress parts of this somewhat large pipeline into a nicer and more robust version. And I think that is a very viable path to do that. So rich ground for future work is what I would say. All right, I will move on. We talked about this slide. So let's talk results. So here are some comparisons with previous work. The most notable comparison is between the original MindEye method plus the MindEye with this new brain optimized inference stage. So we can see that while both are generally very high quality, when we do this additional brain optimized inference step, we inch a little bit closer to both the structural content and also just the idea of the original image. For example, the left column, the building, we get the clock back by doing this brain optimized inference. The plane fixes its orientation. The bike is a better orientation. For the vase towards the right, we recognize and split this vase into sort of two entities. We get closer in that regard. And overall, we're just pulling back some of the original details that are sort of lost when you are primarily doing a clip-based decoding program. Because the problem with clip, again, is that clip describes a very wide distribution of images. And we can refine it a little by providing some low-level blurry structural guidance, but really what we can get closer than that. And that's part of what this inference stage is doing, is it's taking the already pretty good guess of clip and refining it to be a narrower space within the possible family of images that clip can describe that is more brain optimized. So to really evaluate this, we talked earlier about how image feature metrics are a poor approximation of human perceptual similarity. So let's measure it. We conducted a couple of human evaluation experiments. We're trying to really quantify this human perceptual similarity that we're implicitly using as sort of a motivation and a target. So we conducted two experiments, of which the task of the experiments is the same for both of them, which is shown on the right. We show the subjects three images. We say, this is the reference image. Which of the two images is more similar to it? And all of our experiments are shuffled together, and the image order is shuffled, so there's no bias in the presentations. But the two experiments we conducted were a two-way identification experiment. So we showed our results versus a random reconstruction from our results. In other words, could subjects identify which reconstruction corresponded to the correct reference image? The other experiment was, we wanted to know, is this brain optimized inference process really getting us perceptually closer to the ground truth compared to just the base MindEye decoder? So are we improving upon the base model at all? And the answer to both questions was yes. We showed that subjects were able to identify whether the reconstruction correctly identified the image 95.62% of the time, which, as far as we know, is a new state of the art. The only other paper that performed this type of experiment was the original paper from Takagi in late 2022. They did an experiment for the first version of their paper that went to CVPR, and they got like 82%. And that was the only other paper that performed this type of experiment. So we're improved results in that respect. The second experiment, designed to test whether we improved over MindEye, showed that our reconstructions were preferred about 57% of the time. So not massive, but definitely a sizable and statistically significant bump in perceptual similarity compared to the base method.
All right, the first one is, it's your reconstructions versus what? What is the two-way?
So we're going to take the actual reconstruction for the reference image, and compare it with a random reconstruction from a different reference image. In other words,
Okay.
are our reconstructions good enough to identify that they match the reference image?
Yeah.
Yeah, and that's a pretty easy task, and the reconstructions are good enough at this point to where subjects get that right the vast majority of the time, hence the 95%. I would like to have a different way to measure like perceptual accuracy rather than just two-way identification. I think it was useful at first when the sort of decoding space was not very fleshed out and the reconstructions were inconsistent and pretty bad, but the decoding space has matured to a point now where it's pretty easy to identify which one matches the reference image, even if the reconstruction is sort of perceptually very distant. And so I'd like to, in future work, design a better way of measuring human perceptual similarity that isn't two-way identification. But that's what we have for now. Yeah, we also evaluated quantitatively. So this is just the traditional image feature metrics. And compared to MindEye, we see that we are very, very close for the majority of the metrics. We do edge over slightly in terms of some of the higher level metrics, but really a lot of these are statistically very close, which shows that even though we do this additional optimization process, we're not optimizing for image feature metrics and they don't really improve that much. What we optimize for explicitly are the brain correlation scores on the bottom, which understandably improve considering we explicitly optimize for that. But overall, the feature metrics not improving that much, I think tells a pretty clear story about the disconnect between perceptual similarity and similarity measured as far as image feature metrics are concerned. And I think we have gotten to the point of evaluation in decoding methods where these image feature metrics, while informative, are not really that useful for distinguishing the minor differences in reconstruction quality as assessed by humans.
So to interrupt, I guess, the interpretation from this, I could see it going different ways. Maybe one is that, because you're using the encoding model, and I guess this is the kind of framing that you're putting out, because you're using the encoding model to optimize the reconstructions, in theory, these should be more aligned with the actual perception that the subject is actually seeing when they see the image. Is that correct so far of me saying that? Is that kind of the idea
Yes,
of using the encoding model?
The reconstruction target for this work is notably different than in previous works in that what we are explicitly targeting is we are targeting the perceptual similarity of the reconstructions. In other words, me as a human, I want to look at two images and say, look, I did a good job. And you can do that with other works too, but it's difficult to quantify because human raters are more expensive than running your reconstructions through an algorithm. And also it's, people take it less seriously because it's not a hard reproducible number, right? If I run an image through an artificial neural network 5 times, I'm going to get the same result 5 times. And that gives people, I think, a false sense of confidence that it is that number is like a fixed, meaningful measure. But my argument is that if your reconstructions had been 3 pixels different, maybe you would have scored worse, right? These image feature metrics are very sensitive to small aberrations in the image and to small variations in your diffusion generated reconstructions. And I think that's especially problematic when we use diffusion models, which are inherently stochastic. And if you don't like lock the seed or constrain your distribution width in some way, your diffusion model is going to spit out images that might score wildly different on these image feature metrics. And so I just don't think they're that good of a way to evaluate reconstruction quality anymore. They are still useful, but not as useful as I think people imagine them to be.
But I think Paul's question was, are we getting improvements on human judgment? Is our interpretation that you get improvements on human judgment metrics by optimizing for brain correlation specifically? But the idea being that perception is ultimately rooted in the brain activity that we're trying to predict.
Yeah,
so
I think that's exactly the motivation.
Like that would be the cool, interesting interpretation, but there's probably other technical things that.
Yeah, I guess to be a bit more specific, like the brain correlation stuff, that's kind of like given that that's going to be improved upon because you're using the encoding model itself to make those metrics get better. And then the sort of 2AFC between MindEye versus this optimized inference MindEye, are you using that outperformance as evidence that you're actually tapping into that internal mental representation better? Or is that separately just to say that like the reconstructions, more generally speaking, are improved using optimized inference?
So I want to be careful with my wording here. I think it's dangerous to say that we are tapping into the internal perceptual states of the people who had their brain scanned, because we really don't know what those internal perceptual states were. And it would be great if we could have a one-to-one comparison of, okay, here's this person's brain, they looked at an image, I scanned it, I make the image, and then I ask the same person, does this look like the image you saw? That would be ideal. But practically, that's not possible. NSD was collected years ago. The subjects are living their lives. And even if we could get them, I think it's impractical to assume any accuracy for an image they saw years ago, right? So that's not a thing that we can really test or measure. But what we can do is measure whether different humans perceive the image to be a perceptually accurate reconstruction. And we have to make a small assumption here, which is that different humans perceive images in similar ways. Which I think is a reasonable assumption to make, just based off of you and I can look at the same pair of images and both conclude that, wow, those are similar images, right? Human brains are learning to do a similar type of feature extraction to perform this internal calculation of how similar the images are. And so the goal of the brain correlation metric is, if we train a model to essentially do the same thing humans are doing, to take your external image and to map it into internal brain activity, or in our case, a conscious perceptual state, then that mapping will hopefully be more aligned to what humans are doing than a neural network that wasn't trained in this way. And so, yes, the hope is that by using an encoding model that is sensitive to brain-specific features, it will hopefully extract the same features or a similar set of features that you and I are implicitly doing when we look at an image and estimate its perceptual similarity.
Okay, yeah, that makes sense. I will push a little bit and say, like, one interpretation is that, because you're using this encoding model, it's allowing you this novel sort of looping fashion to get the reconstructions to look better ultimately. The other is that maybe there's something in this pipeline that is more so biased towards realism at the expense of low level. So like even these metrics for the low level are doing worse than the original MindEye. But if you have an A-B similarity, like pick the more similar looking image, humans might be biased to pick the image that looks more realistic rather than the one that is more similar in terms of like pixel correlation or color, more generally, or texture, right?
I would
So I'm
argue that
wondering if like
that is a
maybe
bias
it's
that is
getting
present in
pushed.
every single part of every decoding pipeline that exists. In other words, the diffusion models are biased to produce naturalistic outputs based on their prior. The decoding models are trained on naturalistic images, and so are biased to produce images that look naturalistic, even if sometimes they're bad at it. The encoding models are biased in the same way as the decoding models, in the sense that they are trained on naturalistic images, and so that's what they recognize best. But the problem with all of those things is that you cannot escape the prior of your model, right? Your model is only sensitive to the data it is trained on, including the encoding model, including every other part of this pipeline. And so while it is completely correct to say that perhaps this pipeline is biased towards producing naturalistic images and those just score better perceptually, I would say that that is also true of every other decoding method, and that if that is the case, that they simply score better because they are more naturalistic, then we should not see an improvement in perceptual scoring using our method, because every other method is also having this same boost, essentially. And I think the only argument that you could make in that regard is that because we are doing this iterative process, there is, I guess, more model outputs that could be biased, and so they stack. But
hold on, Paul. I had a slightly different understanding of what you were saying, maybe, than Reese. Maybe you're basically saying that the encoding model, which is frozen, it might generate better predictions when images are more naturalistic because it was trained with natural images. Was that the idea? So that there's a bias towards naturalism baked into the encoding model, given the way it was.
I think there might be a bias towards more realism, not because of the encoding model, but because of how you are increasing the strength of the image to image as it goes on. or through some other means that are kind of more complex hidden in the pipeline. But in some way, biasing it more towards the high level versus the low level. And basically what Reese was saying before is that every decoding approach has this thing, but also we've been trying to figure out this trade-off ourselves, right? Like we had multiple versions of the original MindEye model that, changed the strength parameter. So like if I cared only about optimizing for high level, or if we believe that there's a bias in humans for a two-way identification task, we would also probably tweak that knob to be more towards the high level. Like that could be like if we were targeting getting an A/B test to work with humans, we wouldn't, try to optimize for the pixel correlation being that high.
I think it's also important to note here that playing with the strength parameter does more than just affect your naturalism levels, in the sense of really what we're talking about implicitly is adjusting the distribution width. Because when the strength parameter, when you drop the strength parameter to use more structural input, you are incorporating more of that structural input into your output images, but by definition, you also have to then constrain the distribution of your outputs. And so you don't get to independently tweak the naturalism knob and the distribution width knob. And my claim would be that both of these are important. And so we can't tweak a knob to try and affect our levels of naturalism without also compromising the meaningful width of our output distribution. And I think this is the core problem with all existing decoding methods, is that because they output just a point estimate, we have no way of gauging the width of their certainty, right? Because if we decode a single image, what I really want to know is how certain are you in that decoded image? If you froze your seed of your diffusion model and output a single image, then I'm not confident that your model is actually like, I'm not confident that your model has learned how to produce that exact image. What I think has happened is that your model has learned how to make a clip vector that approximates that image, and that we force the diffusion model to spit out the same one every time. In other words, I think we are over specifying our outputs. And an important thing to note for these evaluations is that we didn't lock the diffusion model for any of these, and that we gauged all of these metrics on multiple images sampled from that output distribution. And so we aren't constraining to a single image that maybe has a naturalism boost from having this strength parameter input. We are gauging and measuring our accuracy on all images sampled from this distribution. And I think that's important for the meaning of the naturalism prior boost.
Yeah, when you say the other models are outputting a point estimate, like, yes, we've been using single images for the evaluations, and I believe all the other models as well. But it's not like the model itself only can output point estimates, because it's just the diffusion model. You can feed it the same thing and get a different output. So like maybe we should be evaluating on distributions is kind of what you're.
I think the more more to the point, like we want to have some method for evaluating the width. There has to be, we need some way of ground truthing what the strength parameter should be, like a normative principle, other than this looks about right. I think that's what most people are doing. That's what we were doing certainly early on, is like, what should the strength parameter be? Something around this value seems to produce nice things. I mean, when you're sort of piloting an analysis. But it would be nice if there was a principled way of adjusting the strength parameter so that the decoding distribution had the right amount of uncertainty associated. And what is the right amount? And Reese had a good idea, I think, which is that, well, when you pass samples from that distribution through an encoding model, you should replicate the amount of noise in the brain data. That's a simple idea. It gets a little complicated because there's various kinds of noise in the brain data, some of which you don't want to replicate, some of which you do. But that it would be nice to have, a principled way of doing that.
Yeah, this is a very big open question in our research that we're actively working on. And I would love to take feedback on it and get ideas for the ways we can measure this uncertainty, because I think this is really a path that the decoding space will start to move down, and a path I want to tread down myself. And as we get sort of closer to the ceiling of how good fMRI reconstructions can be, I think this is a rich area for future work to try and add a new dimension to these reconstructions of not just how accurate can they be to the point estimate of the brain's content, but also how accurate can we be to represent the width of this distribution that should be meaningful in correlation with both perhaps the perceptual state of the observer, but also just the neural variance that the brain must admit. And so I think there is progress to be made on that front. All right, we're ready to move on. So we can dig a little deeper into this iterative process and sort of what is actually happening to these images as we go across. These are just a couple of examples, but every column on this chart represents a 10% drop in the strength parameter, which is the rate at which it decreases in our search pipeline. So that's why towards the right side, all the images sort of look very similar, because below strength parameters of about 50%, you start to get very, very similar outputs. But overall, we can see that as time progresses, they get generally closer to the ground truth. And really, we're pulling out some of the relevant details from the original image that were not originally described by the clip vector. And I think this is an illustration of that there is data in the brain that cannot be contained in a clip vector that is useful for the output. And it's difficult to describe exactly what is being optimized, but I think it's clear from these images that the results are becoming perceptually similar and are capturing details that originally a clip vector cannot encapsulate. For example, the person in the middle there sort of gets vaguely closer and closer to looking like the same person, even if it's a clip vector can describe a family of people that might be in this image. By refining the outputs and dropping the distribution variance so that we actually can constrain on this person that was in the image, we get closer and closer to a person that looks perceptually similar. And I think we see that across these images, and we pull out a lot of the relevant details, like the blue sky diagonally coming down in the skier picture, things like that. There are finer details that can be pulled out in this process that direct decoders in their current form have not been able to retrieve. We can also look at sort of what's happening to these actual brain correlation scores as we go over time. The most interesting part of this graph is the dip from the original MindEye base method to the first iteration of our search. And the reason that happens is because the MindEye method that we're comparing against and using for this chart is doing the best of 16 image selection at the end of their pipeline. They generate 16 images and they use a cosine similarity with a disjoint clip vector to pick the best one according to their decoded representation. And that actually works pretty well at improving your brain correlation scores a little bit. There's presumably the data in there that is mirrored in the brain's representation. And so those images that have this additional layer of selection do score better as measured by brain correlation and as by all other metrics. And so that actually gives a slight boost, but because of the way this pipeline is designed, we're using a diffusion distribution that is described by the base clip vector without this extra selection step. So we have to start from behind a little bit in this optimization process in order to perform this optimization. But we do quickly surpass those brain correlation scores. And for all brain areas, we see a gradual improvement over the process that slows down over time as the strength parameter makes the images change less and less. But overall, we see a very stable improvement. And it's also
sorry.
Yeah. It's worth noting that the black line is the one that is actually guiding the search in this plot. That's the NST general mask of the whole visual cortex.
I think I brought this up to you when we chatted before, but I'd be pretty curious to know, like, roughly how many, if you take like the average number of loops that you do for this approach of yours, and you equate that to, like, instead of using pick the best out of 16 for the original MindEye, you pick the best out of whatever the number that equates to the average number of loops that you would do, whether that by itself, like, improves things a lot or not. Because we never tested that. We just kind of arbitrarily picked 16 because that's what we could fit on the GPU.
Yeah,
But
I'd love to run this test Perhaps we can collaborate on this when we have more time after the MindEye V2 work is done. But I think it would be a great test to just see, hey, if we take base MindEye and we generate as many images as are generated on average in the search process, which is about 200 from my estimates. Like, this process is quite expensive with how many images it generates during the search. It has to be to get a good estimate of the space described by a diffusion model. So it is adding a lot of overhead and a lot of additional images to choose from in regards to what the output might actually be. So if we could change the MindEye knob from 16 to 200, maybe we would see a boost there. But I do think we would run into the same wall of there is only so much information that a clip vector can describe. And so if we're using sort of a disjoint clip vector as the optimization for this best image out of a batch selection, then I think we would still run into the wall of there's only so much information contained in that vector, and we are missing some of the original signal in the brain data. But it would be a great test, and I would love to perform it. I think it would be an interesting result. Yeah, any other questions on this slide?
Yeah, I just had a minor question. I'm wondering what the ceiling is here. Like, what is the brain correlation for the actual image passed through the encoder?
That is a question that we actually looked into extensively during my last work, which was called Second Sight. We used that as a way of sort of, if we have surpassed the score of the ground truth image, then it's a clear marker that we are within the space of being correct, either that we're overfitting to our encoding model or just that we have reached convergence with the ground truth image in terms of the brain representation. And the idea there is in practice, that number is about 0.5. That's just sort of about where the level of brain correlation, because there's a lot of noise in brain data, and we're taking correlation between lots of voxels which don't have a lot of signal in them. So that's sort of why it maxes at 0.5 and not higher. But in practice, yes, there are lots of samples that when you pass the reconstruction and the ground truth image through an encoding model, you get very similar results. And we can see sort of a convergence to that. And in practice, about 30% of the samples during the search process will actually surpass the score of the ground truth image. So there is some interesting results there. And I would encourage you to check out my previous paper, Second Sight, if you're interested in sort of that metric and how that's calculated, because we did some analysis for that in that paper.
Okay, super interesting. Cool. I'll definitely look at that.
All right. We have a different plot measuring convergence here. This isn't using the ground truth image. This is using our stopping criteria, but it's a similar idea of how fast do different brain areas reach sort of the stopping criterion threshold, and also the different amount of samples that might reach that threshold. So we have on the y-axis is the percent of samples that have converged by our autoencoder defined stopping criterion metric. And each of the lines is a different brain area. The black line is the one that actually dictated the stopping criterion during the search. So that's the one that matters most for this analysis. But we did it for all the other brain areas, calculating the brain variance within that area specifically. And we can see that higher level areas outside of early visual cortex converge a lot faster towards these variant stopping criteria, which intuitively makes sense because these regions are primarily encoding semantic content, which is enforced in the clip guidance that MindEye spits out. And we use the same clip vector through the entire process. So it makes sense that we would have those samples or those brain areas converge faster for the variance thresholds, because they're admitting the same amount of variance the whole way, essentially, for the semantic content. But for lower level areas, we see a slower convergence, which as we drop the strength parameter, slowly rises, but not as fast as the higher level areas. And I think that's simply because early visual areas admit a lower amount of variance, period. They're much more sensitive to the fine structural details of the presented image, so they're just not going to converge as highly. But overall, we do see a gradual improvement in the amount of samples that are reaching this threshold over time. To talk more about the distribution aspect, we sort of went into this earlier, but I think it's important to recognize the limitations of the tools we are working with in this decoding space. And as diffusion models have gained popularity for this task, I think we have to come to terms with the fact that these are inherently stochastic models. They output distributions, not point estimates. And by most decoding methods, which lock the seed and spit out a point estimate, we are ignoring this fact, which is it's fine for the purposes of evaluation, but I think we are missing potential here, and that these are tools that can be used to describe a more rich representation of your output. And by using them that way, I think we can create outputs that are more descriptive of the brain activity patterns that evoked them. So there's also the problem of just single images can't provide the same level of description of a perceptual state or a pattern of brain activity that a distribution can, which is one of the advantages of decoding this way, is that as the space improves and we get better at decoding distributions, they will be more informative of the thing we are trying to decode. One thing that we haven't really talked about during this work, but that I think is sort of lying in the background of all of this research and this motivation, is that we're laying the groundwork for future decoding tasks, right? The eventual continuation of this field of research is not going to be a brain camera, because that is not a useful thing. It's going to be decoding models that are applied to interesting and hidden states, things like mental imagery, dreaming, resting states, things that right now we don't have ground truth stimuli for. And in order to be able to actually decode these, this is the type of innovation that the field needs. We need better descriptions of perceptual states and uncertainty, and we need ways of evaluating reconstructions that don't depend on image feature metric accuracy to the stimulus image, because those are not available in these cases. So a lot of the motivations for the things that were done in this work were sort of implicitly motivated by the fact that we want to eventually extend these to tasks like mental imagery and more interesting decoding domains. This method right now has some other limitations, one of which is the compute bottleneck. The problem with doing brain optimized inference like this is that there is really no way to get around the fact that you have to make a lot more images. And you can use more efficient image generation models, a lot of which have come out this year. So perhaps future work can optimize a lot doing that, but there's no way to escape the need for this additional inference cost. And so I would like to explore future work that can bake some of these optimizations into the decoding process more directly, so that we get the same sort of benefits without necessarily as much of the cost. But right now, that is a limitation of this method. We also talked about the stopping criterion and its limitations, but the main problem with it is that it's destroying a lot of the brain noise that is useful for estimating the neural uncertainty that we want our distribution to capture. And so I would like to design better methods for this that don't destroy as much of that noise and can actually provide a verifiable and more useful estimates of the perceptual uncertainty of the observer. That will be especially relevant for extending these cases to things like mental imagery, which are carry a lot more of that perceptual uncertainty. When you imagine an image, it is a lot less clear and a lot more sort of structurally ambiguous than when you see an image. And that is a difference that will need to be reflected in those decoding cases when we try and extend models to them. But yeah, I think that we need decoding models in this space to tackle a new target, right? We have gone far enough tackling the imaged feature metric tables that outperform every other metric by some arbitrary neural network. I think we need to create outputs that are optimized to be perceptually similar to their stimulus images, or if not perceptually similar, we need to develop a better way to measure the difference between images. But that's a problem that has existed for decades in computer vision, and I don't foresee an easy solution to it. And I think that the best way to circumvent it for now is to use the miracle of evolution that is the human brain to perform our evaluations, which is, in my opinion, more accurate to the real target. We also want to capture that uncertainty, which we talked about, and build on this method to hopefully be better and more efficient. So that is my presentation. Thank you. Looks like we have a couple of last minute questions in the chat. Paul, do you want to just ask yours?
Oh, I was just commenting on Connor's observation that, the Meta's MEG reconstruction blog post shows like videos of the outputs.
Yeah.
But it shows like a video of the decoded output, but it's actually like for the different MEG time points. But you could do a similar thing what you're saying, like show.
In previous presentations, I have made animations of distributions. You can definitely make them. They look pretty cool. They also look different for if you take like the convergence thresholds for different brain areas. So if I take the the pattern of images that is produced in a distribution when sort of V1 converges versus when like the higher visual cortex, which is the areas outside of early visual cortex, when those converge to the stopping criterion, those two distributions look very different in their amount of and in their distribution width and the differences between images, and you get sort of very interesting comparisons there. So yeah, very interesting things to
Yeah,
look at.
I really love this idea of like using the encoding model to optimize like the eventual reconstructions. And that's kind of like, the dream of these kind of projects, right, is to get the reconstructions to be as similar to the mental representation, right? And so I think like that's kind of what I was briefly questioning about of like, does the theory of using the encoding model suggest that you should be getting closer and closer to the mental representation, even though I know you can't actually measure that. Like you can't do an MTurk task and figure out if that's actually close enough to get the original participants. But I guess
in principle, that is the theory, yes.
Yeah, but I guess potentially a future project, right? But to really, like, I would really love to see some sort of experiment that is tapping into that. And for instance, show the person an image, have them look at it, and then you reconstruct it, and then like you show it back to them along with the original image. And maybe the reconstruction is so much more similar to their mental representation that it's actually regarded as the original image rather than the actual seen image from before. And like that would maybe be evidence that you're actually tapping into the mental representation because they're mistaking it for the original image, even though it's not.
That's a great idea for a behavioral experiment. So basically you expose subjects to a ground truth image, and then some amount of time elapses, and then you show a reconstruction and the actual ground truth image, I don't know, an hour later, right? So maybe the reconstruction is closer to their compressed memory of the ground truth than the actual pixels are, and that would be a case in which they would choose the reconstruction.
I would love to perform that. I think it would be very interesting. I think there are also a number of challenges, which is that you would need to already have a good enough model of that person's brain in order to perform the decoding task in essentially real time. And this is obviously not something that was possible when NSD was released, because NSD was the first real data set of this large enough scale to do these sort of tasks. But maybe in the future, when more data sets are collected, this is something that can be sort of tied to the data set collection, is that once we have enough data to make a model of their brain and sort of do the transfer learning of these existing models to the new brain space, then we can do some real-time reconstructions and get some actual perceptual accuracy numbers.
Yeah, it wouldn't really have to be real time. Like you could just do it like after they leave the MRI machine.
Yeah, not like real time, but as far as the it's like quote unquote real time, like an hour later during the same session.
Exactly. I mean, the bigger barrier is maybe like right now the reconstructions are often looking kind of wonky. You can tell that it was a reconstruction and not a real like image.
Mm-hmm.
So, after that barrier, I feel like people are, especially in the next year or so, like the reconstructions are going to be indistinguishable from what a real photograph looks like. Not like one-to-one pixel kind of accuracy, but like you wouldn't be able to tell which one is the
they're going to be naturalistic enough, yeah.
Diffusion model output. But once you get past that, that could actually be, I think, feasible. Of like that would be, because this is the issue, right? We have so many metrics. We don't know what metric is actually the best to use. If you only target low level, then you have a problem. If you only target high level, then you realize that 2AFC judgments are actually maybe a better way to target that than the high level. Something that we talked about last week was that the new MindEye version 2 reconstructions can outperform on the high level metrics, but they don't look as good. So it's like, what are the high level metrics really meaning if subjectively they look worse, but the high level evaluations say that they look better? So
yeah, and I think that's the core question we're trying to address with the coding tasks is, what are we really optimizing for? What are we considering to be the best reconstructions? And I think that's an open question, and one that this research sort of tries to explore a little bit. But going forward, I think it's a useful benchmark to have both in your work, right? We want to evaluate the feature metrics so that we have some hard number to compare against previous works, but we also have to recognize that it's a little bit stochastic and it maybe doesn't have as much statistical power as we thought it did. And there are other ways we can explore that, such as human experiments, and I'm sure new ones will be invented going forward. I think also brain correlation is going to be a decent approximation for the type of human perceptual similarity that we're performing in these experiments. And that's not something that we really look too hard at for this work, just because we explicitly optimized for it. So it's less of a fair comparison. But I would love to do some work in the future that does some actual research to see if brain correlation better approximates human subjective perceptions than other image feature metrics, because my intuition says that it probably should.
That could be done pretty easily in a model-free way, and maybe people have done this, but you can make RDMs for using these feature metrics, using brain activity patterns, and then compare them to actual human judgments. I mean, it could be that the feature metrics are better if the MR data is too noisy, but at some point, the brain data should converge. Like it should surpass other, or be as good as any other metric.
Yeah, and I think it's really down to the quality of your encoding model as well. We haven't had encoding models that have been this good for very long, right? The quality of encoding models that have been trained on NSD are a lot better than the ones that came before it. And so when trying to move images into the space of brain activity to measure this correlation, I think that boost in encoding model quality is going to be a big part of it. And you're right that I think that there is a critical mass of encoding model performance where the brain data will have an inherent advantage and it will be a better measure of perceptual similarity. And the question is just, have we crossed that barrier yet? I would argue yes, but we're going to have to do some experiments to show that.
I feel like something related to this is used currently in some of the practice of doing this RDM analysis. Like, I think we looked at a paper in a previous lab meeting, maybe from Talia Konko group or something, where they do like reweighting of DeepNet features using an encoding model before computing the RDM as a way of comparing models in a, so it's like feature reweighting by brain encoding as opposed to using the raw features, and reweighting always does better for matching the brain data.
Oh, that's cool. Yeah.
I mean, it's kind of by construction, but.
Oh, for matching the brain data, not the perceptual data.
Yeah.
No,
Yeah. Brain data is by construction. Perceptual data, yeah.
That would be a result.
Yeah. So yeah.
Yeah, I would say we have one result consistent with the idea that brain optimization optimizes for perceptual similarity. It's one result, it's consistent. There are other alternative explanations. A lot more work has to be done. The interesting interpretation is sometimes not the right one. Yeah, but we'll see.
We have the first glimmer of a result pointing at this conclusion, but more work is needed to solidify it. I agree. All right, any more questions?
It's nice.
I guess, what are the future directions that you're going with? Are you continuing to improve this pipeline, or?
I've been working on this project for the better part of a year now, and if I am completely honest, I am sick of improving this pipeline. So I think there are a number of things that I will be doing in the near future. My main priority, we have some mental imagery data, and so I'm working on fleshing that out for a publication. We have some results that show that mental imagery reconstructions generalize fairly well from vision data. We have mental imagery data from the NSD subjects that we're fleshing out, so we're working on that. I would also like to do that brain correlation approximates perceptual similarity research. I think that would be, if it works out, it would be an interesting conclusion and one that would be not that hard to show. So that's an interesting idea. And then my other main priority is to continue fleshing out this uncertainty research, trying to quantify the amount of neural and/or perceptual uncertainty from brain data. Right now, we have a very preliminary way of doing that with the stopping criterion for this work, but there are undoubtedly better ways to do it, and there's a lot of theory and experimentation that will have to go into that research. So I think that's a rich ground for future work that I plan to explore as well.
Yeah, very exciting. I really can't wait to see the future of like mental imagery decoding using these approaches. And you'll be the first to be showing that off, I suppose. So that'll be super exciting.
Yeah, there is another data set that has a couple of mental imagery trials that had a paper come out a couple months ago. So we won't be like, it will be the first for NSD because we have that data privately, but there are some other data sets that have some mental imagery results that are being reconstructed now with modern methods.
Mhm. I assume that being able to use NSD would give you a higher ability to
Oh yes,
decode.
I can say without a shadow of a doubt that our reconstructions are significantly better than the other paper that doesn't have NSD. So
Cool. All right, thanks so much for presenting with us. This was really fantastic. And yeah, thank you. Thank all the people who joined us, and Thomas for you coming as well.
Yeah, it was great to meet all of you. Thanks a lot.
yeah, thanks for the opportunity. This was a fun presentation.
Yeah, thanks so much, Reese. And also thank you to your group for the NSD dataset. I love that dataset. Thank you very much.
Good. It's good to hear. Thanks.
Yeah, the NSD dataset is really incredible. And, you know, I wouldn't even be in my current job position if it wasn't for the release of NSD.
Oh,
So
cool.
like
I'll
the
pass it on to Kendrick too.
so like the ability to have these giant data sets to use with the new machine learning methods, it's really like opened up a new door for these kind of projects. So
Yeah, good. That was the explicit goal when we wrote the grant for this, and it's great to see that it's working out as planned. That's really lovely.
yeah, and probably, you know, with that demonstration, I feel like now it's more obvious than ever the need to collect these giant kind of generalizable data sets.
Yeah, there's a lot of efforts, ongoing efforts.
Yeah, there's like Things Initiative, multimodal data sets. It's really a good time to be, I think, in this area.
Yeah, agreed.
Now we need mental imagery data sets.
Yeah,
Yeah.
we're trying
Hard to
think.
collect, but worth it, I think.
Bye, everyone. Great talking to you.
Yeah, great talking. Thanks, everyone.
All right.